Hello everyone, my name is Gyanendra Singh and today I'll be presenting my capstone project on mobile price range prediction, which is a supervised machine learning project based on classification. So let's start with the project summary first. So mobile phones have become a necessity for every individual nowadays, and people want more features and the best specification in their phone, and that too at a cheaper price. Mobile phones come in all sorts of prices, features, specifications, and all price estimations and estimation and prediction is an important part of the consumer strategy. Deciding on the correct price of the product is very important for the market success. Uh, market for market success of a product, yeah, and a new product that has to be launched must have the correct price, so that the consumer will find it appropriate to buy that product. So in this data science project, we've aimed to predict mobile price range based on their sorry uh, based on their based on their specifications using machine learning algorithms. The dataset consisted of various features related to mobile phones, such as battery capacity, RAM, internal memory, and many more. The dataset was splitted into training and test datasets and several machine learning algorithms such as logistical regression, decision tree, regressor, random forest, and support vector machines were applied to the training dataset. So, and the random forest algorithm was chosen as the final model due to its high accuracy and F1 score. The project concluded that the predictive modeling can be an effective approach for the mobile price range reduction, and highlighted that the importance of the data pre-processing and the feature engineering for improving model accuracy. So our target variable over here in this project will be the price range. So about the problem statement, in the competitive mobile phone market, companies want to understand the sales data of mobile phones and factors which drives the prices. The objective is to find out some relationship between features of a mobile phone, for example RAM and internal memory, and its selling price. So in this problem we don't have to predict the actual price, but a price range which indicates like how high the price is. So about the data descriptions, we have battery power, we have blue, which says that whether it has Bluetooth or not. Clock speed is speed at which microprocessor executes its instructions. Dual SIM states that uh, whether it has dual SIM support or not. FC is front camera in megapixels. 4G is whether it has 4G or not. Int memory is internal memory in gigabytes. MDEP is mobile depth in centimeters. Mobile weight, n cores, number of cores. PC is primary camera in megapixel. PX height is pixel resolution height. PX width, RAM, screen height, screen width, talk time. 3G, whether it has 3G or not. Touch screen, whether it has touch screen or not. Wi-Fi, which says whether it has Wi-Fi or not. And about our target variable, which is price range, it has 4 categories, which is low cost, medium cost, high cost, and very high cost. So thus our target variable has 4 categories. So basically it is a multi-class classification problem. So first of all, we'll start with importing the libraries like pandas, numpy, matplotlib, and seaborn. and then we'll mount the drive and um, provide the path of our data set, and then we'll read it using pd.read underscore csv. So this is what the head of the data set looks like, and this is how the tail of the data set looks like. So about our data, say shape of our data set, it has 2000 rows and 21 columns. Next one, if we'll check the statistics of the data, like count, mean values, standard deviation, minimum, other quartiles of the 3 quartiles, and the maximum value. We found out that the minimum length of screen width and pixel height. See, we can see over here the mean length, sorry, minimum, the pixel width, sorry, pixel height, and sorry, and the screen width is actually 0, which is not possible in any mobile actually. So there is a mismatch in this data, so we need to handle this. So let's first just check like in how many observations the screen width is 0, so it came out to be 180, and now we'll check like in how many observations the pixel height is 0, which came out to be 2, right? So what we'll do, there are only 2 observations with pixel height 0, so what we'll do, we'll just drop it. And about the screen width value, which are 0, which were 180, we will handle them using nearest neighbor imputations. So we'll apply KNN imputer. So how it works actually, it takes the missing values, the missing values are imputed using the k nearest neighbors approach, where the Euclidean distance is used to find the nearest neighbor. So in this method actually, before imputing we replaced the 0 values with the NaN values. So that's what we have did. We replaced all the 0 values with the NaN values, and then we have applied the KNN imputer. So now if we'll check the shape of the data set, it is 1998 and 21 by 21, and we'll check how many observations have screen width value 0. It came out to be 0. So it shows that we have handled the mismatched values, right? Now we'll again check the data types of and the non-null values. So we can clearly see there are 0 null values over here, and all the data types are in float data types. So we don't have any object data type in our data set, and also we have 0 null values and price range. So, and as we've said, that price range is our target variable. So now we'll check for the null values to be sure. So it came out to be 0, and we will visualize it also, and it came out to be 0. We cannot see over here, like there is none, there's none. Okay, so now we'll start with our exploratory data analysis. So we'll take a look at our target variable first. So there are 4 categories, as we have said, like low cost, medium cost, high cost, and very high cost. So we first of all check the value counts of all the categories, which came out to be, for high cost it is 500, for low cost it came out to be 500 again. So we can see that we have almost an equal number of observations for all these for each category. Thus I don't think we don't have an imbalanced target variable. So accuracy score will be the best evaluation metrics for us to select the model actually, right? So here with the representation visualization also, we can see that there is an even split between all the 4 categories. So now we'll check the correlations between the dependent variables and the other independent variables. So here we can clearly see that the RAM has the highest correlation with if you can see, that RAM has the highest correlation, highest positive correlation with the price range, which is 0.92. And also we know that the mobile with the high RAM are very costly, and thus RAM increases the price ranges of any mobile. Also, we can see battery power also has a positive correlation, right? Battery Yeah. Again, we can see that the battery power also has a positive correlation with the price range. Generally, mobile phones having high prices comes with a good battery power, right? And also pixel height and pixel width are positively correlated. So generally, price range of a mobile phone have good resolutions also. And 4G and 3G are highly positively correlated. Nowadays most of the smartphone have the both has both type of options, so that might be the reason they are highly correlated. And the next one is primary camera um, and the front camera are positively correlated. So every phone, like each, like most of the phones nowadays comes with the both cameras, so that might also be the reason. And why screen height and screen width are positively correlated, because yeah, it actually represents the dimensions of the phone, right? Next, we'll start with the univariate analysis of the categorical columns. So we can clearly see over here for the categorical columns, um, we can see over here for all the categorical columns like Bluetooth, dual SIM, 4G, 3G, Wi-Fi, and touchscreen. There's a good split between all the five, apart from 3G. Like few of the phone, uh, like very few of the phone doesn't have 3G. So yeah. So 1 means it has the specifications, 0 means it doesn't have the specifications. So the percentage distribution of the mobile phones with Bluetooth, dual SIM, 4G, Wi-Fi, and touchscreen is almost 50%, like I've said, and the very few mobiles, 23.8%, do not have 3G in them. Now we'll try to find the relationship between the RAM, battery power, pixel height, and pixel width. So we can see with respect to the price range. So we can see with the higher RAM, we have the higher price range, right? And we can clearly see over here with the higher battery power, we have the higher price range. For the higher price range, we have the higher battery power. So for the higher price range, we have the higher pixel height as well as pixel uh, width, right? So mobile phones having RAMs more than 3000 MB or 3 GB, around 3000 MB, has falls under very high cost category, as the RAM increases the price of a mobile phone, and also the RAM having less than 1000 MB falls under the low cost category. And the mobiles with battery power more than 1300 mAh has high cost, very high cost. And the mobiles with battery power between 1200 to 1300 mAh falls under the medium and high cost category. And mobiles with more than 700 pixel height and width more than 1300 has like high cost range, comes under high cost range. Now we'll try to plot all the features. Yeah, the features with the supported or not supported mobile specifications, which were the Bluetooth, the dual SIM, 4G, 3G, touchscreen, and Wi-Fi. So this is the observation. These are the observations, right? Now with observation with the price range, right? Next one is the price range grouped by their number of cores, yeah, and their mobile depth. So the observations we can see from the above graphs is that we can see that each price range category has equal number of mobile phones having both supporting and non-supporting specifications. From these two graphs we can infer that there is a very few mobile phone in the price range 0 and 1 with lesser number of cores, yeah, right, and most of the mobile phones in the price range of 2 and 3 with high number of cores. So the number of phones with less thickness is high, and count with the phone with high thickness is actually low. Now we'll check the numerical features that is driving the price range. Which of the numerical features is driving the price range the most? So yeah, okay, so we'll plot a trend line, box plot, yeah. So what we'll do, we'll plot a line plot over here for all the features, given features, which are numerical features, which are battery power, clock speed, their front camera, internal memory, etc. So here are the visualizations we can see with the line plots for the battery power, the clock speed, the front camera, yeah. So what are the observations we can infer from these is for class 1 and class 2 battery power range is almost similar, and as the battery power increases, price also increases, which is quite obvious in my opinion. Mobiles in very high price range, which is class 3, has less weight compared to other classes. That means as weight of the mobile decreases, the price also increases, right? And mobiles having maximum screen height and width falls in very high price category. We can see in the line chart also that screen width and screen height from the class 2 screen width and the height starts increasing with the price, right? And similar in the similar cases with the pixel height and the pixel width, as the resolution of the screen increases with the price also, right? Next one is the RAM has clear relationship with the price range. We saw that in the correlation matrix also. So now we'll check the specifications we will check the further specifications of 3G and 4G. So first of all, we'll check whether they have 3G and 4G or not, 3G and 4G or not. So when they have both of them, we'll just check into it. So as we can see, for low cost to very high cost, mobile phones have both the features. So for most of them, they have both the features, right? Mobiles with 3G will check. Mobiles with the high cost only comes with mobile with high cost have more the number for the high cost. So mobile which has very high cost very less likely to have 3G, and there are more chances that the high cost mobile will have 3G, right? Mobiles that does not have 3G and 4G, we can check over here. So it's obvious that the low cost mobiles will not have 3G and 4G, and mobiles with very high cost may have 5G, and as you know, the technologies changes every time. So about the number of cores with respect to price range, we can see that price range 0 class category 0 has majority of phones with 2 cores, Price range 1 has the majority phones, 1 and 4 cores processor. Price range 2 has 4 processors, right? And price 3 has majority of phones with 5 and 7 processors, right? Next one would be mobiles with 4G features, yeah, with Bluetooth features, we can see. So majority of phones from the price range from 0 to 2 don't have Bluetooth features, and on the other hand, the price for the price range 3, they have Bluetooth feature. Let's check the distribution of the numerical columns and the outliers. Okay, so what we'll do, we'll plot the box plots and the distribution for all the numerical columns, and we'll check for the outliers. So here we can see for battery power there is no outlier and it is evenly distributed, kind of. Yeah. Here we can see for front camera there are few outliers and it is right skewed, slightly right skewed. Yeah, and for the pixel height also it has few outliers and it is slightly right skewed. Anything else? No. So we can clearly see data is well distributed for only two features, which were a front camera and pixel height. They both had few outliers. So what we'll do, we'll treat those outliers, okay, and after treating the outliers, removing the outliers, we will try to visualize it. Yeah, here we can see for front camera and pixel height it is now free from outliers, right? So now the data shape has 1962. So we've actually removed the outliers, right? Okay. After removing the outliers, you can see the shape of the data set is 1962 and 21. Again, so we have handled the outliers. So what we'll do, we'll start with the feature selection, and before that what we'll do, we'll copy this data set into a new data set, and then this is what the head of the data set looks like. Again, we'll try to find the correlations, and yeah, so the RAM and the price range has the same correlation, right? And price range and RAM, yes. So next what we'll do, we will check the feature scores, and so we will start with the feature scores, and yeah, so here which feature score has the highest? So RAM has the highest score over here, right? So what we'll do, we'll select 12 features with highest chi-squared score, in which we can clearly see the RAM has the highest score, and following with pixel height, battery power, and pixel width, right? So now we'll split the data. We'll start with the predictive modeling before the splitting the data. Sorry. We'll start with the predictive modeling. So the algorithm we'll be using for this predictive modeling will be decision tree, random forest, gradient boosting classifier, k nearest neighbor classifier, XGBoost classifier, and support vector machines. So as a decision tree, random forest, and samples tree do not require feature scaling as they are tree based models. So we will be using xtrain and xtest, which are not scaled, and for k nearest neighbors and SME we will be using xtrain scaled and xtest scaled. So that will actually standardize data which will be used to standardized data or scaled data. Now, okay, yeah. So we'll import all the essential libraries first, right? Yeah. So here we can see the scaled data, sorry, extrained scale data here, X, X test scale data, to the splitting actually. So we've splitted the data first, and for in training and test data set, and then what we have got the extra scaled version of the data, which for the X trained and X test also. Now what we'll do, we'll start with uh, the decision tree classifier. So in decision tree classifier, it's actually decision trees and ensemble method actually they do not require feature scaling and to be performed. So they are not sensitive to the variance in the data. So we'll just use xtrain and xtest and ytest and ytrain, which are not scaled. So first of all, we'll apply a decision tree algorithm without the with the default hyperparameters only, right? So this is the confusion matrix for that, and the observations which we have acquired are that the train set accuracy is 100% and the test accuracy is 84%. The model is overfitted uh, and on the train data set, and did not generalized as well. We will tune the hyperparameters to reduce the overfitting first and then try to improve the model performance. So uh, we'll do the hyperparameter tuning here. So yeah, so first of all we'll apply grid search CV and we'll fit the model with it. Yeah, here, okay. So there were a lot of fitting to be done. So it's taking so long. Yeah. So grid search CV has been done, has been estimated, done, estimated and done. So maximum depth came out to be 6, and the criterion was entropy. Yeah. So accuracy score came out to be 0.9, sorry, 9, around 98%, and accuracy score for the test data or the predicted test y test data came out to be 85%. We can see the confusion matrix over here, right? And yeah, and now we'll see the feature importance. So RAM came out to be the highest. RAM came out to be the highest important feature for which was responsible for the price increase, right? So we will perform multi-class ROC curve. We can clearly see that AUC value for class 0, which was low cost, is 0.9614. For class 1 it is 0.8785, for class 2 it's 0.8872, and for the class 3 is 0.9422. So what are the observations that we have inferred are that the train accuracy has been reduced to 98% from the 100%, and the test accuracy has increased by 1%, right? So somewhat reduced, and so somewhat we have reduced and overfitting the overfitting by reducing the training accuracy, and it will not be a good model for us, so to say. And RAM, battery power, pixel height, and width came out to be the most important features. And this model classified the class 0 and class 3 very nicely, as well as we can see in the AUC. It's almost 96% for both the classes, whereas in for class 1 and class 2 it is only 88%, right? And now we'll move ahead with our next classifier, which is a random forest classifier. So we will start with the default parameters only, without the hyperparameter tuning. So we've splitted the data. Accuracy score came out to be 1, which is 100%, and the accuracy score for the test data came out to be 88%. Yeah, so this is the confusion matrix. Train accuracy is 100% and test accuracy came out to be 88%, which is good, but we'll have to but it seems to be model seems to be overfitted. So what we'll do, we'll need to reduce the overfitting by and improve the model performance. So what we'll do the hyperparameter tuning and reduce this overfitting. So after doing the hyperparameter tuning, okay, we can clearly see after hyperparameter tuning, RAM, battery power, pixel width, and pixel height came out to be the most important features here also. From the ROC curve, now we can see that the AUC value is almost like for class 0 and class 3 it is almost 100%, and for class 1 and class 2 it is 96%, which is a good observation, which is a positive thing for us. So observations which we have got are: before tuning it was training accuracy was 100%, test accuracy was 80%. After the model was actually overfitted, so what we have done is tuned the hyperparameter. So after tuning it came out to be 100% and 90%. So we have slightly improved the model and overfitting is slightly reduced. From ROC curve, it is clear that the model has poorly performed for the classes class 1 and class 2. We can see it is only 96%, which is better than the better than earlier, but decision tree, sorry, but it is still it is less, right? Now we'll go ahead with the gradient boosting classifier, and here we have again splitted the data, and the accuracy was 100%, and the accuracy accuracy score came out to be 90%. Yeah, okay. This is the confusion matrix. Okay, so yeah, so the confusion matrix. So the accuracy difference was about of around 10%. So what we'll do, we'll tune the hyperparameters again, and after hyperparameter tuning, the feature importance. Okay, yeah. Now we are getting to somewhere, because for all the classes we are getting a very high value of AUC. See, okay. So before tuning it was 11%, now it's 10%. Yeah. So ROC curve, we can clearly see that the biggest difference is for class 0 and class 3, for which class 0 and class is 96% and 90% respectively. It is also good, 96% and yeah. For next one will be the k nearest neighbors, for which we will be using the scaled train data set or and test data set, right? So first of all, we'll start with the default hyperparameters only. So the accuracy score for the trained data set came out to be 75%. Accuracy score for the test data set came out to be only 59%. So there seems to be overfitting, right? And we can see over here from the ROC curve also that for class 1 and class 2 it is very less IUC value. So what we'll do to reduce that, to overcome that overfitting and to improve our model, we'll do some hyperparameter tuning. So that's what we have done. And the n nearest neighbor came out to be 29. Yeah. Now the test accuracy score for the trained data set came out to be 76%, and the test data set, the accuracy score came out to be 70%. This is the now ROC curves, yeah, improved values, right? So surely we have improved the model performance and reduced the overfitting, but however this is not the best model for us now. So yeah, we can clearly see the difference, right? The before hyperparameter tuning and after the hyperparameter tuning. So next one would be our XGBoost classifier, which in which the default hyperparameter will continue with the default hyperparameter. Yeah, and with default hyperparameter, the accuracy score for the train set came out to be 100%, and for the accuracy score for the test data set came out to be 90%. And yeah, okay, 98% and 90% again. Let's do some hyperparameter tuning to to improve our model. So after hyperparameter tuning, yeah, the accuracy score for the trained data set came out to be 100%, and for the test data set it came out to be 90%. From the AUC scores we can also see some improvements. Yeah. Feature importance, RAM came out to be the most important feature, we can clearly see. Okay, from AUC ROC curve it is clear that the model has the almost correctly predicted for the class 0 and class 3. Last would be our support vector machine. Okay, last would be our support vector machine. So the accuracy score for the trained data set came out to be 98%, and for the test data set it came out to be 89%. Then to improve it, we've done some hyperparameter tuning, and after which okay, accuracy came out to be 98 and 97%. Okay, and the ROC curve actually has the highest value of AUC, right? And yeah, the feature importance, if we look into the feature importance also, the RAM came out to be the highest important feature. So the observations which we have made are the accuracy score is 98.5% and test score is 89%, was 89%. The model seems to be overfitting, fitted, as the difference between the train and the test accuracy score was almost 10%. So after hyperparameter tuning, the accuracy remained almost the same at 98.3%, and the accuracy of the test score, actually train accuracy, remained the same, but for the test accuracy it increased to 97%. So SVM actually has performed very well as compared to the other algorithms. In terms of features, feature importance, RAM, battery power, pixel height and pixel weight came out to be the most important features, and the F1 score for the individual classes is also very good, and area under curve for each class prediction is almost 1. So I'll just reiterate, I'll just quickly go through all the observations and the final observations that we have made, right? So again, what we'll do is we'll cross check the data, whether the data is good for SVM or not, by creating four um, data frames for each class, and plotting the scatter plot for the most important feature, which are RAM and battery. Yeah, we can clearly see over here the scatter plot between RAM and battery, sorry, battery and RAM. uh, yeah, here battery power and RAM. Okay, optimal feature, we optimized it for RAM and battery. So yeah, so what are the conclusions that we have inferred after all this? Is that we have started with the data understanding, data wrangling, and basic EDA, where we have found the relationships, trends between price range and other independent variables. We selected the best features for predictive modeling by using K-best feature selection method by chi-square statistics. We've implemented various classification algorithms, out of which SVM, support vector machine algorithm, gave the best performance after hyperparameter tuning, with 98.3 for the train accuracy and 97% for test accuracy. XGBoost is the second best model we have got, and which was after hyperparameter tuning, with 100% train accuracy and 92.25% of test accuracy. KNN gave a very worst model, proven to be the worst model performed, and we've checked for the feature importances for each model, and RAM battery power came out to be the most important features. With this, I would like to say thank you so much. Thank you.